Hello, good morning everyone. Today we are going to continue our discussion related to functional dependencies. So today we'll be going through few examples and we'll see how to identify functional dependencies given the instances of the relations, and further we'll discuss closure of set of functional dependencies. So before we go for new concepts, let us have a recap. In the last session, we had a discussion about the functional dependencies. So what we mean by functional dependency? Given the relation schema R, we are having the set of attributes alpha, which is subset of R, and another set of attributes beta, which is also the subset of R. Then we say that there is a functional dependency alpha determines beta, or beta is functionally dependent on alpha if and only if for any legal relation R on R, if there are two tuples, say T1 and T2. If T1 agrees upon alpha, then if T1 and T2 agrees upon alpha, then T1 and T2 also agree upon beta. So this is the formal definition for functional dependencies. So if there are two tuples in the relation T1 and T2, and if these two tuples agree upon the values of alpha, then the same two tuples T1 and T2 agree upon the values of beta. Then we say that there exists the functional dependency from alpha to beta. So this is the formal definition of functional dependencies that we have seen. Further, we have discussed one special case of functional dependencies, and we said that the functional dependency K determining R, if there is a functional dependency K determining R, then this K is a super key of relation. Why? Because this group of attributes denoted here as K determines all the attributes in relation R. Right? Further, we have gone through few types of functional dependencies, under which we have seen the very first type, that is the trivial functional dependencies. So we say that the dependency alpha to beta is trivial if beta is subset of alpha. So for example, A determining A is trivial, AB determining A is also trivial. Okay, so if there exists a functional dependency alpha to beta such that subset of alpha, then we say that it is a trivial functional dependency. The next kind of dependencies we had a discussion about is the partial functional dependencies and full functional dependencies. So what we mean by partial and full dependencies? So let us assume once again that there is a relation schema R and we are having two subsets of R. So X is subset of R and Y is also subset of R. And we are having a dependency X determining Y. So this dependency X determines Y is full functional dependency if and only if there do not exist any proper subset of X, say W, such that W also determines Y. So if there is no proper subset of X such that that subset also determines Y, then we say that X to Y is full functional dependency. In contrast, if there is a dependency X to Y and if there exists a proper subset of X such that the subset, let us assume it is W, such that W determines Y, then it is partial functional dependency. So if there exists a subset of X, say W, which also determines Y, then this kind of a functional dependency, we say that it is a partial dependency. The third kind of dependency that we have seen is transitivity, transitive dependency. So if we are having a dependency, say A to B, and also if we are having a dependency, say B to C, then we say that there is a dependency from A to C, right? And if this is the case, then we say that this is a transitive dependency. So this is a kind of dependency. So we had a discussion about all those concepts in the last session. Today we are going to discuss characteristics of functional dependencies used in normalization. So we are listing out the characteristics of functional dependencies used in normalization. So there is a one-to-one relationship between the attributes on the left-hand side, that is the determinant of the functional dependency, and those on the right-hand side of a functional dependency. So what we mean by this? See, for example, if I am having a dependency, say A to B, then what it indicates, A is the determinant. Left hand side of functional dependency is called as a determinant. So in this case, A is my determinant, right? So always there is one-to-one relationship between the attributes of LHS and RHS of a functional dependency. This means that if I am having a relation with these two attributes, say A and B, and if I am having several tuples, so say for example for tuple 1, I am having the value of attribute A as A1, right? And if the value of B is B1, let us assume, right? Then for the attribute value A1, always I am having the same value of B1, a same value of B, that is B1. So there exists one-to-one relationship. So always if I am having A1 for some other tuple, then my B value must be B1. So one-to-one relationship. Okay, but if we consider from right hand side to left hand side relationship, the opposite direction relationship, then it can be one-to-one or it can be one-to-many. What does this mean? See, if I am having always, if I am having the B value as B1, I am having the value of B1 here and the value of A is A2. So my functional dependency A to B is valid. My functional dependency from A to B is valid for this tuple wherein I am having the A value A1 and B value B1, and for this tuple also wherein I am having A value as A2 and B value as B1. But if I look at the relationship from B to A, that is from right hand side to left hand side, for B1, I am having multiple values of A, that is A1 or A2. So it can be one to many from right hand side to left hand side. Are you getting me? So if we talk about left hand side to right hand side, it should always be one to one. But if we talk about right hand side to left hand side for the same functional dependency, it may be one to one or it may be one to many. Right? So that is one of the characteristics of functional dependencies we are making use of in normalization. The second characteristic says that the functional dependencies, those we are defining based on the semantics of the attributes. These functional dependencies hold for all time, for all instances of the relation. So if I am having a functional dependency, say from A to B, this should be valid for all instances of my relation. Okay? And the third important characteristic that we should understand is the determinant has the minimal number of attributes. So what is determinant? The left hand side. So the determinant has the minimal number of attributes necessary to maintain the dependency. Or in other words, we may say that the functional dependencies, those we encourage in normal, must full function side that also determines my right hand side. So we are going to prefer the full functional dependencies as far as normalization is considered. Right? So keeping these characteristics of functional dependencies in mind, we are going to look at few examples for identifying the functional dependencies. Right? Given some instances of the relations. So let us assume that we are having this relation schema, instructor department schema, wherein we are having the attributes like ID, name, salary, department name, building and budget. Right? Now, let us assume this instance of the relation, that is instructor department schema. Right? And we are having this one instance of this schema. Now, by looking at this instance, what are the functional dependencies those we may infer given the relation schema and the instance? So by looking at, by observing this instance, can we identify few of the functional dependencies? How to infer dependencies? Look at the semantics of the attributes. Find out the relationships between the attributes referring to the schema and referring to this instance. So what is the functional dependency that we may infer? We are having so many relations. name, ID determines salary, ID determines department name, ID determines building, ID determines budget. Can we have this functional dependency? Whether the ID of the instructor determines name? Yes, I want responses.
Yes, ma'am.
Whether ID determines name?
Yes, ma'am.
Yes.
Yes, ma'am.
Whether ID determines salary?
Yes, ma'am.
Yes. Whether
I.
ID determines department name?
Yes, ma'am.
Yes.
What about building and budget? Whether ID determines building? Yes.
Yes, ma'am.
Yes. And whether ID determines budget also?
Yes, ma'am.
So, can we have this functional dependency based on this schema and this instance? Obviously, yes. So, we
Yes.
can infer the functional dependency like ID determining name, salary, department name, building and budget. So, actually, ID is determining all the attributes, all the remaining attributes in this relation. Right? Similarly, if I look at the dependency like department name determines building, whether it is valid?
No, ma'am.
No. Department name determines building. Is it a valid dependency?
Yes. Yes,
Why?
ma'am.
Why?
I think no, ma'am.
See, what we mean by functional dependency? From left hand side to right hand side, there should be one-to-one relation. Is that correct? So if
Yes, ma'am.
I find this dependency like department name is determining building. So let us look at value physics department, whether the building is same for physics
No.
department. Yes or no? We are talking about this dependency. Department name is determining building. So I am having here two tuples for department name value equal to physics. Right? So what about the value of building? Whether these values are same or different?
Same.
These values are same. So if my department name is physics, the building must be Watson. Is that clear? If my
Yes, ma'am.
department name is physics, then the building must be Watson. So it is one-to-one relationship. One department is not located at two different or many different buildings. One department, one building. If I look at this computer science department, so I am having three tuples here for computer science. So whether for all these three tuples I am having the same value for building? Yes or no?
Yes.
So may I say that department name determines building?
No, ma'am.
Why? If I know
Because,
the
ma'am,
department name, If I know department name, is it not possible for me to identify the building?
But ma'am, biology department name also having building Watson. So you have told that a one-to-one relationship should be there, no?
One to one from left hand side to right hand side.
Okay, from then it
From
will
right hand side to left hand side, it might be one to one, or it might be one to many, right?
okay, ma'am.
So I may not have the functional dependency like building determining department name. This is not a valid dependency. Building determining department name. Why? Because if I consider this building name as Watson, right? Now, how many tuples I am having for building name Watson? 1, 2, only 2, 1, 2 and 3. Is that correct? So, if this is my tuple 1, let us assume this is my tuple 1. So, if my tuple 1 is having the building value Watson, so this is my alpha and this is my beta. To and if these two tuples agree upon alpha values, then they must agree upon beta values. Right? So if I'm looking at these two tuples, whether they agree on alpha value, that is building, yes, they agree. Why? Because Watson, the same alpha value we are having. But what about beta? What about beta value? That is the department name. In tuple T1, I am having department name as physics, and for tuple T2, this is my tuple T2. So for tuple T2, I am having the department name as biology. So my T1 beta is not equal to T2 beta. My T1 beta is not equal to my T2 beta. Is that correct? And that is why this condition is not satisfied. And therefore, I may say that from building to department name, this functional dependency is not valid. But if I look at this dependency, department name determining building, it is valid. Are you getting me?
Yes, ma'am.
May I proceed? So what about this department name determining budget, whether this is valid dependency or not? Yes. Is this valid dependency or not? Department name is determining budget. Yes, it is valid because one department is having only one budget, right? It may not happen that one department is having different values for budget, right? So department determining budget is also valid, right? So by looking at such kind of instance, you should be able to identify the possible functional dependencies based on the semantics, right? Is there any doubt so far? Is there any doubt? May I proceed with the next?
Yes, ma'am.
Fine. One more instance, one more example to identify functional dependencies. So see here, by giving such kind of an instance, you should be able to identify the dependencies. So here, For this particular example, we have identified 5 different functional dependencies, and these dependencies are A to C, C to A, B to D, AB to E, and BC to E. So I'm not going into the details how we have identified this, but this is an exercise for you. You should try to understand how we have inferred those functional dependencies based on this instance. Right? So I'm giving you this exercise. You try to understand why we are saying that these are the valid functional dependencies for this instance. Right? Now, let us proceed with the concept of closure of a set of functional dependencies. Closure of a set of functional dependencies. So usually we have been provided with a relation schema R and a set of functional dependencies capital F. So given a set of functional dependencies for schema R, there are certain functional dependencies. Those can be logically implied by this set F. So what we have in this set F? In this set F, we are having the list of functional dependencies. Right? Those hold for this relation schema R. So given this set of functional dependencies, it is possible for us to derive few more functional dependencies. Those can logically be implied by this given set F. Say for example, if in my set of dependencies, the C. Let us assume I am having these two dependencies. So, by applying certain rules, it is possible for me to logically come up with a new functional dependency like A to C. So, these two may give me a new dependency like A to C. Right? So, what I am saying is, given a set of functional dependencies, it is possible to logically infer other functional dependencies based on the given set F. Right? So, given a relational schema R, a functional dependency small f on schema capital R is logically implied by a set of functional dependencies capital F on relation schema R. If every relation instance R on R satisfies F, will also satisfy this new functional dependency small f. So, to come up with all such functional dependencies, those can be logically inferred by the given set of functional dependencies F. We are having certain rules. So let us go through these rules and let us name the new set that we may come up with by having all such functional dependencies. Those can logically be inferred by given set F. So, once again I am repeating, if I am provided with the set of functional dependencies F, then if I come up with few more functional dependencies, those can be implied by this F, then we may come up with a new set of functional dependencies, and that new set of functional dependencies is denoted as F plus. And this new set F plus is called as closure of a set of functional dependencies F. So closure of F is denoted as F plus. So we are having this original set of functional dependencies F. We go on adding the FDs. Those are logically implied by this set F, and we come up with a new set of functional dependencies, and that is F plus. And this F plus is known as the closure of a set of functional dependencies. So to compute this closure, that is F plus given F, we are having certain axioms, or we are having certain rules, and these rules are known as Armstrong's axioms. So let us see these rules. So let us list out now these rules. If beta is subset of alpha. So what is beta and alpha? Given the relation schema R, I am having alpha which is subset of R, and I am having beta which is also subset of R. So if beta is subset of alpha, then we may infer the functional dependency alpha to beta. And this kind of functional dependency that is inferred if beta is subset of alpha, this dependency or this rule is called as reflexivity rule. Secondly, if I am having a dependency in my set of functional dependencies of the form alpha to beta, then I may infer another dependency like gamma alpha determining gamma beta. So simply we are augmenting the attribute or set of attribute to both LHS and RHS of the dependency. So if I augment some set of attributes, say gamma, towards both LHS and RHS, I may come up with a new dependency, and that is gamma alpha determining gamma beta. So this dependency or this rule is known as augmentation. One more rule we are having, and that we have already gone through. If alpha to beta and beta to gamma exist, then we may come up with alpha to gamma, a new dependency. And this rule is known as transitivity. So in our Armstrong's axioms, we are having these three important rules: reflexivity, augmentation, and transitivity. Right? So given the set of functional dependencies F, we are applying these Armstrong's axioms. Right? So given the set of functional dependencies F, we are applying this Armstrong's axioms to come up with the new set of functional dependencies F plus, which is my closure of set of functional dependencies F. Right? And what are these three important Armstrong's axioms? The first rule is reflexivity, the second is augmentation, and the third is transitivity. Right? So what is reflexivity? If beta is subset of alpha, then alpha determines beta. If alpha determines beta, then gamma alpha also determines gamma beta. And if alpha determines beta and beta determines gamma, then alpha determines gamma. Right? So reflexivity, augmentation and transitivity. These three are important Armstrong's axioms or rules. Those can be applied on the set of functional dependencies that we have, and we may come up with the closure of a set of functional dependencies, which is denoted as F plus. So what we have in F plus ultimately, we will be having a given relation schema R, right? And how to compute this F plus? Given F, we need to apply Armstrong's axioms to come up with the dependencies. Those can be logically inferred by set F, and we come up with a new set of functional dependencies F plus, which is known as closure of the set of functional dependencies F. Right? So the final comment regarding these rules known as Armstrong's axioms. So these three rules are actually sound and complete. So what we mean by this? The rules are sound, meaning these rules generate only the functional dependencies that actually hold. So all the functional dependencies, those can be generated or those can be inferred by Armstrong's axioms are valid functional dependencies. So these rules are sound. They generate only the functional dependencies, those actually exist. And these rules are complete, meaning these rules generate all functional dependencies that hold, all. So by applying these rules, it is possible to come up with all the functional dependencies that hold for given relation R. Right? So these are very important concepts, and based on these rules, we are going to identify this F plus, that is the closure of the set of functional dependencies. So these are basic Armstrong's axioms. I hope you must have understood the concepts. If no, please let me know. Is there any doubt? Yes. Any doubt? Have you understood what we mean by Armstrong's axioms? Let me give one example. Suppose I am having relation schema R with attributes say A, B, C, D. Okay? And let us assume that we are having the functional dependency, set of functional dependencies. Say A to B, B to C, and sorry, B to C, and suppose one more C's. Right? Now, we can add few functional dependencies and we may come up with a new set F plus. So we may apply these rules. So let us first try to understand this augmentation rule. So if I am having this functional dependency say A to B, then if I augment D to both of these sides, so if I write AD to BD, So what I did, I augmented one attribute to both the sides of the functional dependency, and I come up with a new dependency like AD to BD. So this is a new functional dependency that can be inferred from this A to B. So this can be added in my F plus. Are you getting me? Yes? Are you getting me?
Yes, ma'am.
If I am
Yes, ma'am.
having A to B and B to C, I may infer applying transitivity A to C. So this is a new dependency that I am adding, that I am inferring out of the basic ones. Is that correct?
Yes, ma'am.
Yes,
Fine.
ma'am.
So about reflexivity, if beta is subset of alpha, then we may say alpha determining beta. What does this mean? Beta is subset of alpha. Beta is right hand side, right? And alpha is left hand side. So if I write the dependency like AB determining A, here my beta is subset of this alpha. Then by reflexivity, this dependency is valid. So I am inferring this dependency, AB determining A. Right? So by means of this reflexivity, I may add this dependency in my set F plus. So this is how we need to generate this F plus. In the next class, we are going to discuss few more rules. Those can be formed based on these basic rules. Right? And then we'll try to solve few examples based on this concept of F plus, and we'll see what actually is motivation behind creating such closure of set of functional dependencies. Why in fact we should have this F plus? What is the use of this closure of set of functional dependencies? Right? So we are going to discuss these concepts in the next session. So I hope you must have understood the concepts. So let's stop today. Thank you.